All right, now that we're recording, so 1-4 angles, we're starting off with a ray. So it's a part of a line containing an endpoint and a side that extends indefinitely in one direction. So again, it's if you had a line that goes on forever in both directions and you cut the end off, it would then form a ray. So a picture to illustrate this, if we had this here, that would be a ray. Now it has points A, B, and C all on this ray. So even though it's a ray, I can still say that A, B, and C are collinear because they're all found in a line. You can be collinear on a line, you can be collinear on a ray, you can be collinear on a line segment. As long as it falls in a line, you are collinear. So A, B, and C are collinear, but these points have certain importances over the other. All right, so I'm going to give a name for this ray, and I'm going to show you a few different ways that we can do it. So first, I'm going to call this ray A, B. That would identify this ray here. Another name I could call it would be ray AC. That is also a name for the ray. If I don't want to write the word ray, I would have to have some sort of symbol to identify that it's a ray. So I could do AB and then draw a ray on top. So on one side it has the arrow, on the other side it ends, it terminates. And then AC, same thing. So those are 4 possible names for this ray. Now some names that are not applicable to this ray. I cannot call it ray BC. I cannot call it ray CB. I cannot call it ray CA. And that's because when you identify a ray, you have to start with the endpoint that terminates, because that is identifiable. I know that this thing starts or stops, however you want to look at it, at A. From there, it goes on forever. So calling it B, C, D, E, F, excuse me, there's no way of knowing where those points are. I know A starts it, and then it just goes on forever. So you can call it whatever you want as long as you start off with that first point on the ray, the terminating point, and then whatever other point is on that ray, you can then put it in its name. So all rays have to start with that endpoint, and then any other point with either the symbol or the word ray with it. Now angles, we know what angles are. That's when we have some amount that we can measure. But an angle is formed when we have 2 rays that connect at their endpoints. Now those points are going to have a specific name. We'll get to that in a moment. I'm going to go ahead and write what I just said there. So we have an angle forms when 2 non-collinear, that's a technicality that I'll talk about in a minute, rays have a common endpoint. So an angle forms when two non-collinear rays have a common endpoint. Well, why would I throw that word in there of non-collinear? Well, in math, you have to think of everything that could happen. And if I just made a blanketed statement that says when two rays connect at the endpoint, they form an angle, technically there is one thing, well, actually two things that could happen that prevent an angle from being made. So I'm going to draw you two pictures that show why these rays cannot be collinear. They have to be non-collinear. We'll call it an error. So error number one. So what would it look like if two rays were collinear? So if I have this ray here that exists, and I have another ray that shares the endpoint and is collinear, that means that they form a line. So I'll do this in a different color. We'll do it in red. So if it shares the endpoint and is on the same line, what just happened is that I have the same ray. There is no gap between the two rays, so it didn't lift at all, and there's nothing to measure. This, you could argue, has an angle of 0. If it has an angle of 0, it has no angle. So an angle isn't formed when they are the same line. The second error that could happen. I'm going to start off with the same ray. Now, how else could these rays be on the same line? Well, if they're the same ray, they'd be on the same line. And also, if this ray opened all the way back up, shared the same endpoint, and again, was collinear, what we have now is a horizontal line. It's just a straight line. This, again, is considered to not have an angle. Now, when we go to measure it, we could actually get that it has a measurement of 180 degrees. So there is a degree measurement that we could have, but technically this is not an angle because it goes against our definition of two non-collinear rays. So even though I can measure this, and that's 180 degrees, it's not considered an angle in mathematics because these two rays are collinear. So that means that 0 degrees and 180 degrees are not actual angles. They're degree measurements, but they're not considered an angle. It's kind of like Pringles are not considered a chip. Bring that back. Oh, we didn't talk about that? Oh, the hyperbolic paraboloids? The Pringles is technically a snack and not a chip because it's made from a potato mash, and where they were invented, chip is a snack, is not necessary, but snacks are necessary for living. And so Pringles, the way they're made, are classified as a snack food, not a chip, so they don't get taxed. Yeah. I forget what rants I go on and when, so there's a little fun fact for you. Okay, so angles form when two non-collinear points share a common endpoint. We've used this word before, but we'll bring it back. And that's going to be our vertex. That is, in this case, the endpoint of a ray. So when we want to know the vertex of, let's say, an angle, it's going to be at the endpoint of the ray. So when we have two rays that meet at the endpoints, they're going to be forming this vertex, and it's the vertex where you find the angle. So it's where an angle is found. So it's at the endpoint, and obviously an angle is formed when you have two rays that are not collinear, so they're not the same thing, they're not aligned, and they then form an angle at the vertex. Just a general example. So this is what it would look like, an illustration of, a representation of two rays that share an endpoint that are non-collinear. So as a result, they have formed an angle. That angle is right here. Now that little arc that I just drew, that's usually the symbol for an angle. Much like how we have congruent marks, if I had another angle with another symbol that, I would know that those angles were equal to each other, that they were congruent. If I wanted to show that I have a second one, I would just do a second arc in there. So it looks something like that. But for now, we have an angle, and that's formed at the vertex being the two endpoints of these rays at point A. This top ray, I'm going to call ray AB. Which I can also call it being the side AB. And so that ray now becomes a side to my angle. This one over here, it was ray AC, and now it's going to become side AC. And I still want to recognize that it's a ray, so I'm not going to say side ray AC. I'm just going to say, hey, it's a side, and that side is AC, which is a ray. Point A, which is the endpoint of both rays, is our vertex. And then again, we have our angle. And sometimes what happens in geometry is that they begin to label these angles numerically. So I'm just going to label this angle number 1. So this is just our first angle because we only have one angle. So how would I name this angle? Kind of like on how I have AC with the ray on top, or if I had AC with a line segment on top, or AC with a line on top, that's a way of labeling. So I know that there are 2 points, A and C, on either a line, a ray, or a segment. We can do the same thing with angles, but there's a few different ways to name an angle. This symbol here, it looks a lot like the angle that I just drew. It also looks like the less than symbol. It's going to be a slanted line, and then it becomes horizontal. So it really will look like an L that's just bent. So that is the symbol for an angle measurement, or rather just an angle, and I'm going to say angle A. So if I said angle A, I know that I'm talking about that angle. Again, it's not like that. That would be less than A. It's slant, horizontal, and then A. So that's just a way to distinguish it from other symbols. I named it the first angle. So I could all call it angle 1, because there's only one angle with the label of 1, so I can call it angle 1 or angle A. Now, what if I have multiple angles at vertex A? Meaning, what if I just went ahead and I added in one more ray, and I had it be down here, and I had point D. So now I have my angle A, which is angle 1, but now I've just formed another angle right here, and I'm going to call that angle 2. And I put 2 curves to show that it is a different angle than angle 1. So now if I say angle A, am I talking about angle 1? Am I talking about angle 2? Or am I talking about angle 3? Well, where's angle 3, you ask? Great question. Angle 3 is found right here. So when I say angle A, which angle am I talking about? Am I talking about the blue angle? Am I talking about the purple angle? Or am I talking about the yellow angle? So just saying A is not enough when there are multiple angles off of one vertex. So we have another way to name angles. We do that by starting at a point on the side, going to the vertex, and then ending at the point of the other side that makes the angle. We'll call it a little angle sandwich or a little vertex sandwich, because we want to have the vertex in the middle, and on the outside will be the 2 sides. So we know where it starts, where it goes to, and where it ends. So again, if I want to name the angle for angle 1, if I'm only talking about angle 1, and I'll clarify that there. So these are only names for the angle 1. Now that we have multiple angles, if I want to say this angle here, what I'm going to do is I'll start with my angle symbol, and then I'm going to start off with a side, the vertex, and a side. So this is a side, that is a side, and that is the vertex. So we have to have a little vertex sandwich in order to label those angles. Another name could be CAB, because again, C is a side, A is the vertex, and B is a side. So I have 4 different names for that angle. This first name wouldn't really be appropriate, because since I now have 3 angles at angle A, so if you had this situation, I would definitely want to either see angle 1 or kind of this angle sandwich where you have the 2 sides and the vertex in the middle. So some things that we can't call angle A or angle 1. We can't call it angle ABC, because if I said angle ABC, I'm claiming that now B is a vertex and there is an angle that exists right. That's not true, because there isn't a line that goes up to B and then down to C. I can't call this angle ACB, because if I said ACB, I'm claiming that A is the side, C is the vertex, and B is the other side. I can't say that either. So the order of these letters matter, and you want to make sure that the vertex, where the angle is right in the middle, because it's the 2 sides on either side that make that angle. So there is kind of some logic to that, whether you like it or not, tough shenanigans, but we always want that vertex in the middle. All right, so an angle again is formed when two rays meet at an endpoint, and those two rays are non-collinear, so they don't form a line. So when these rays meet, we are going to have three types of angles. And you've probably heard these before. I'm going to add something in on you guys. So what this reads is I put the M in front because when we're just talking about an angle, we use the symbol. When we want to talk about the measurement or the actual value of the angle, we have to put a little M in front of that symbol. So this M means that it's going to be the measure of, and then that is our angle. So I put on a test the measure of angle A, and you told me acute. That would be incorrect. I would actually want to know that the measure of angle A is 65 degrees or something like that. If I said angle A, well, then I'm just referencing angle A, and maybe you told me that angle A is angle 1, or angle A is angle BAC. So when I get rid of the M, I'm no longer asking for a value. I'm just asking for an identification. But when I put the M in there, I'm looking for a concrete response. So when the measure of the angle is equal to 90 degrees, we would have something that would look like this. They'd be perpendicular. That's not what a right angle looks like. When we have a 90-degree angle, we tend to put a little square in there. That square, as we know with squares, they all have 90-degree corners. They all have right angles. That identifies that you have a 90-degree angle. This is considered a right angle. Now, you can never assume you have a right angle unless, one, it says it's 90 degrees, or two, that you see that little symbol in there. If it looks like it's 90 degrees, you can't assume it's 90 degrees because maybe it's 89.9 degrees. Maybe it's 89.99999 degrees. So you can never make that assumption unless it says it's happening. So the first type of angle we have is a right angle. Well, what happens if we have something that is greater than 0 degrees, but less than 90 degrees? So 0 degrees is the smallest possible, but we can't get there because then it would be collinear. So it's going to be something a little bit bigger than 0 degrees. And it has to be something less than 90 degrees because once we get to 90 degrees, then it's a right angle. So an example of what this angle could look like is like the picture I drew on the previous slide. This would be an angle that is greater than 0 degrees, but less than 90. This is what we would label as an acute angle. So if it looks like the angle is less than 90 degrees, then we can say that it is acute. And then the last one is when an angle is bigger than 90 degrees, but less than 180. So something like this. So it's opened up wide. That one is our obtuse angle. So right angles have that little square in the picture. It's exactly 90 degrees. Acute angles are less than 90 degrees, but greater than 0. And obtuse angles are greater than 90 degrees, but less than 180. Now you may be thinking, well, what if you go past 180? So you've at the point where it's collinear again, and then you bend it a little bit more. What sort of angle is that? Well, that would not be considered an angle when it is bigger than 180 degrees, because you would then go to the inside of the line, and then that would form a new angle. So it's still an obtuse angle, but you would always measure the interior part of it, the inside part of the angle, not the exterior, the outside. If you get to higher level mathematics, such as trigonometry and even into calculus, you do use angle measurements that are bigger than 180 degrees. I mean, that's where like the whole like 360 and 720 come in, because you're going around a circle once or more than one time. So that is a possibility, especially with a coil that's winding, of how many degrees does it have to turn, what sort of torque does it have, things like that. So it is possible to work with measurements that are bigger than 180, but the angle it makes cannot exceed 180. So degrees can, angles cannot. All right, so the big takeaways from today, before we get into using a protractor, we have a ray. A ray stops. It starts at a certain point, has an end point, and then it goes on forever. It is a linear model, so it does not bend, it does not curve, anything like that. You can label a ray by using the word ray, and then always starting with the end point. So A, B, A, C, A, D, A, whatever. Or you can write the A and the whatever point with a little ray on top. When we have two rays that meet at an endpoint, as long as those rays do not form a line, so they are non-collinear, then the result will be an angle. Where those rays meet and the angle is formed, we have now generated a vertex. The vertex is our angle. That's where the angle is found. If we find that we have more than one angle at one vertex, then we have to get more technical with the name. The name will be the angle symbol, a point that is found on the side, the point that is the vertex, and then another point that's found on the other side. So we know that we're going from B to A to C. And we have three different types of angles. We have a right angle whose measure is equal to 90 degrees. We have an acute angle whose measure is greater than 0 but less than 90, and an obtuse angle that is greater than 90 but less than 180. That is all the information that you need for the homework tonight. But I want to show you, stop doing that, how to use that protractor, just because I do think that it is a pretty interesting tool, especially for those that are planning on going to something involving construction. Construction, not just like outside, but construction like you're actually building something, you're planning something. You want to be an architect, you're going to need to use a protractor because you need to make sure the angles are correct. If you get technical with being an artist and drawing, you could use a protractor to make sure that if you're doing a picture that deals with depth perception of something, that you want to use the appropriate angle so that everything is going towards the same point and that you're not just eyeballing it. So how we can measure this acute and this obtuse angle. There we go. All right, so I'm gonna go ahead and make this a little bit bigger. Come on. All right, so this point right here is where your vertex goes. So usually there's some sort of indent, or it's open, or there's something signifying that that is where your vertex should be identified. So on this acute angle, my vertex is found right there, right where that bullseye is. I can put my vertex right in that circle. Here, my vertex is right there. So again, I'm going to put it in that little bullseye area. Now, starting off with this cube, obviously I did not draw this angle perfect, that this line is up a little bit. And that is the purpose of this black line right here. That this line says that that should go along one of the sides that you're measuring. So I'm going to take my protractor and I'm going to tilt it. So now the bottom of my protractor is lined up. I have in the bullseye, I have my vertex, and along the bottom here, so along the bottom, it is now lined up with my ray. So to measure how big this angle is, I'm going to look at my protractor and I see what value it's at. Now my smartboard is pretty bad, so I'm going to go ahead and look at my computer, and it looks like it is around just shy of 50 or 130 degrees. So I have to decide which of these two measurements makes the most sense. Well, this is definitely an acute angle, so it's going to be less than 90 degrees. So looking at this 130, that doesn't really make any sense, because 130 degrees should be more than 90, so it should be obtuse. So you ignore the outside track and you look at the inside. Now, if where this line is 50, it looks like it's about 1 or 2 degrees less than 50. So I would say that this angle measurement is probably about 48 or 49 degrees. So it is an acute angle and its measurement is 49 degrees. We would have to ballpark this at that point. So that's how you would use a protractor for this situation. For this one over here, again, I'm going to go ahead and tilt it so that it lines up with my ray. Again, human error, but that's as close as I can get. And so now, I'm going to look over here. Now, I see that it's almost 50 degrees or it's almost 130 degrees. That's kind of crazy that I did that because it's almost identical, but hey, whatever, I'm that good subconsciously. Okay, so with this here, it looks like it could be 49 degrees or it could be 131 degrees. Now, it doesn't make sense that it'd be 49 degrees because that should be acute. So in this case, I'm going to still read the inside track and I see that it's 131 degrees. So this one was 49 degrees, reading the inside track, and this one here, I'm also reading the inside track. The reason for that is because they are both opening up in the same direction. Now, when would I use the outside one? Well, the outside one is if we had an angle like this, where I'm going to line the protractor up on the left side and it opens up to the right. So with this one here, again, I'm going to line up. That looked like it was about 90 degrees. Put it in its place, and there wasn't a little square, so I couldn't assume it's 90 degrees. And it's a good thing I didn't assume, because it looks like, according to the outside track, is right around 91, 92 degrees. And again, I'm doing the outside track because it's opening up to the right. Now, obviously, if we were in person, we'd be able to play with the protractors more and do some activities with measuring. You guys are just going to have to take my word for it, because during this pandemic, we can't do that. Okay, so if it's opening up from the right to the left, you use the inside track. If it's from the left to the right, you would use the outside track.